and she's working under Professor Valerius Karani. So over to you, Pooja.
Thank you so much for having me here. Am I audible to everyone? Is the audio okay?
Yes, you are audible and you're also visible.
All right, perfect. All right, thank you so much. Thanks to the organizers for inviting me to give this presentation. I will quickly go into sharing my screen. Host disable participant screen sharing.
Oh, I'm sorry. Just give me a second. I'll do
No
that.
issues, yeah.
Yeah. Now are you able to share your screen?
Yes, I think it works now. Let me.
Okay, I'm sorry. Yeah, please continue.
No problem. So you can see my screen, I hope. I'm just moving away all the Zoom controls, so okay. Is it okay? Can everyone see my screen? Should be fine, right?
I can see.
All right, perfect. Thank you so much, Ranjit, for your feedback. Yeah. So I will start my talk. Today I will be talking about this very recent paper that some of my co-authors and I put out and recently published in Physical Review Letter. I am not yet a research scholar. I wouldn't call myself that. I'm still a student. I am a PhD student at CQT and US. And I work under Valerius Karani, as it was previously introduced. This work was something that it just so happened to be happenstance, really. It was not really conceived as a project on its own. But I will tell you how it was motivated and how it really just came to be out of nowhere. More importantly, this is the actual title of the talk, simply because even though this is what we wanted, PRL had its own version, and they really wanted to stress the fact that we gave a lot of importance to non-Gaussian states of harmonic oscillators here in our paper. So I will be talking about a witness for non-Gaussian states of harmonic oscillators. Let me break down the title for you in order to motivate. Again, the project, as I said, was not conceived on its own. The idea came from the fact that most entanglement witnesses for harmonic oscillators that we know of were derivatives of Duin criteria of some sort. Duin, Simon, there were quite a few people who had these uncertainty-based criteria where you have, for instance, if you have systems 1 and 2, the state of a system is said to be entangled if the sum of the variances of these terms, that is the position and momenta of both the system, is less than a certain value. But if you were to observe these individual quantities, any classical pure state, the variance of any measurement would be 0. For instance, if I were to naively plug in values x1 equals x2 equals p1 equals p2 equals 0 into these expressions, this is technically possible classically if we do not really limit the precision of measurements. Then this very classical state without 0-point motion would be found to be entangled. In a sense, the criteria of this sort had posed the danger of having false positives to classical theory. So we wanted something that was more akin to, let's say, a Bell inequality, where improper measurements would ensure can only make sure you do not detect entanglement, for instance. But if you were to detect entanglement, you know that the system is quantum, right? So that is one motivation, no false positives from classical theory. That's basically doesn't assume quantumness of the system before going with the witness itself. And secondly is that it's dynamics-based. What we mean by that is all that we assume of the system is that it is precessing about a certain, with a certain frequency. That is it. So it is semi-device independent. We do not assume at the very beginning that the system is classical, quantum, nothing of the sort. All that we do say is we know the dynamics of the system. And in this case, we consider harmonic dynamics, where we know the angular frequency, for instance. Yeah. So this would allow us to easily make measurements on the system by just performing quadrature measurements in optics terms. So these were the motivation for having come up with this project itself. One, that we need a witness that doesn't assume quantumness, and one that is easy to implement in a laboratory. It turns out Tsirelson, very, very smart guy, we all know of, back in, I think, 80s or even before that, had a very, very dusty paper in the archives, which is never published so far. Oh, sorry, not 80s, early 2000s, my bad. How often is the coordinate of a harmonic oscillator positive? So Borel Tsirelson in 2006, with this uncited paper, answered this question of how often is the coordinate of a harmonic oscillator positive, and by doing so, provided a criteria for telling if the harmonic oscillator is quantum or classical. It is brilliant. Let me go ahead with the description of this protocol itself, because it is using this that we come with our results itself. The assumptions on the protocol is the physical quantity X, some quantity, is undergoing a uniform precession at pulsation omega. So that is the only assumption you're making on the physical system itself. You have a system that precesses with with frequency omega. That's it. How do you do the protocols? For each round, you prepare the system in a certain state, any state, rho, and you wait for a duration between one of these three times. Either you measure instantly, or you evolve the system over a period of t/3 and perform a measurement, or you let it evolve to 2t/3 and perform a measurement. You choose one of these time periods randomly, and you measure the system to see if the position of the system is greater than 0 or not. Basically, to see if if your particle, as it's precessing in phase space, is it on the right side or not. Right? And then you perform this over many rounds, and then you ask how often is X greater than 0 for that system. This is interesting because from here we will see that you get some sort of a difference in quantum cases, but the very fact that the time evolution of a harmonic oscillator, a very universal fact, one that was not really seen to have much of a difference in the classical and the quantum case, the fact that you can actually see some difference here was very interesting. So again, to brush up the protocol again, note that we're not measuring the system, the same system again and again. I mean, what I mean is you initialize the system to a certain state, perform measurement, discard. Initialize the system again to a certain other state, perform a measurement, and discard. Right? So that's what you're doing over multiple times. Let's say the initial state was here, you measure, discard, and then you measure, found it here, discard, go on and on. P3 is the probability of finding the particle with X greater than 0, the system greater than 0. It's basically just summing up over t equals 0, t equals t/3, and 2t/3, as I previously mentioned. So doing this, as I've been hinting all this while, there is a classical bound. So classically, there is a bound that you can achieve, which is dependent on how the system was initialized. If the system was initialized to any point in the purple regions, so for instance, here, here, or here, then when you perform a measurement, you will find that maximum, like 1 out of 3 times, you will find that the system is on the right side, right? Like with X greater than 0. So because both the other two purple regions are with X less than 0. So you have a classical lower bound, and similarly, you have a classical upper bound, depending again on where the system was initialized. If it was initialized in the green regions, then the upper bound is 2/3. So let's focus on the upper bound. The bold PC3 is a classical upper bound where a system precessing about with a certain frequency can only achieve 2/3. A similar bound will hold for all odd number of measurements, because if you make even number of measurements, then your bound will just be 1/2. It's symmetric. But with odd number of measurements, then you have this bound. In this case, the number of measurements is 3. The classical bound can also be understood with active and passive rotations. What I mean by that is, Active rotations are simple, straightforward. Again, initialize a system, and then you perform a measurement, and to see where you find the state of the system, if it's greater than 0 or not. But passive rotation, what I mean by that is, if you do know t, since t is an assumption, given the initial state of the system, you can simply perform your measurement operators, like you can rotate them according to t equals 0, t/3, and 2t/3, and you have a probability of success, which you can sum over the positive and the negative and the positive areas by this formula. It's quite straightforward if you give it a small thought, but I'm not going to spend too much time explaining that. So we saw that the the classical case, maximum 2/3. Quantum case, do the same thing. This time by measuring position of pos of x is a projected onto the positive x plane. So you measure the position and see if it's positive, right? I've just written it down in very quantum mechanical language. You are left with the measurement operator, which has this sort of a form. It is in nature a block diagonal of some sort. The maximum value that you can find, the maximum bound, the maximum probability of success in this case would be the largest eigenvalue of your measurement operator, right? That's again quite straightforward, but assuming that there is no degeneracy in your measurement operator, the P3 here is the maximum value that is attainable quantum mechanically. And surprise, surprise, by solving for numerically for a certain truncation, we found that the value P3 is around 0.709, which is obviously greater than 2/3, right? So quantum harmonic oscillators can exceed the classical bound. The next question, obviously, is why? It turns out the reason lies in Wigner negativity. If I were to replace the probability density function in the previous slide that I showed you, where we're performing the passive rotations in order to get the probability of success, if I were to replace the density function there with just the Wigner function, what we know is position and momentum are incompatible observables. Hence, Wigner function can have negative values, right? As long as the marginal sum to 1, you can have any sort of like negative probabilities or negative values in this quasi-probability distribution that we're aware of. And what happens when you do that, when you place negativity in these already sort of negative zones, right? Then when you sum up your overall bound, the overall probability of success increases. So you have P3 infinity, which is basically the maximum possible attained probability of success, which is in the quantum case, it will be greater than 2/3. This is the case. This is the Wigner function plotted for 3 measurements, and this is for 7 measurements. So P3 is greater than P3 classical in the quantum case. Now, all of this is already done by Tsirelson. I know I spent half the time just explaining this, but that work is brilliant. And what we're doing now is to extend this notion in the case of to entanglement of 2 harmonic oscillators. Now, the assumptions are very similar. There is a physical quantity X undergoing a precession at uniform precession at pulsation omega, but now X can be the position of an effective oscillator, which is built out of 2 or more physical ones. What I mean by that is, if you have 2 oscillators with arbitrary masses and frequencies and XX coupling, you can decompose them in normal modes with all this simple algebraic manipulations, where X plus and X minus are the positions of the normal modes, right? Then the time evolution of X sigma, that's X plus and X minus, is a uniform precession around the phase space. So now, instead of considering a single harmonic oscillator and just measuring the position as is of that oscillator, you can instead measure the position of the normal modes, right? Normal modes, and which is decomposed into the modes 1 and 2. And that way you now also have a similar sort of bound, right? So let's see how that works. Again, X is the position of an effective oscillator. The protocol for each round, same as before, prepare the system in a state, wait for a duration between one of these times. T sigma is now the time period of the effective oscillator. Then you measure the normal modes, X sigma. I mean, people might ask, like, how do you measure normal modes? Of course, one of the ways is to measure the modes X1, X2 independently, and then just sum them up or subtract them up according to the expressions. These are the same. This is supposed to be X minus with something, sorry. Anyway, so, or you can also address them directly. There are ways to do that as well in the literature. And now you compute P3, which is again the probability of success for finding your normal modes to be positive using your measurement operator and your X. And if you notice, if you remember the Duan's criteria from before, up to a multiplicative constant, X sigma, for instance, X plus here, is the same as the Duan's criteria, where U in Duan's criteria, where it's just a sum of the positions of the two operators. It's the same here. I mean, sorry, two positions, X1 and X2, and it's the same for X plus as well. Having done all this, what can we tell about the entanglement between the oscillators? I'm just putting some equations here so you remember what I'm talking about. Now, if you realize we were measuring in the normal modes where you have some thetas there, right? So for values of theta equals pi by 4, we found that if the precession protocol, the entire Tsirelson's test for non-classicality, if it's performed for this value of theta, then all states that violate the classical bound for the normal modes are entangled in the physical modes. So if what that means is if this effective oscillator, when measured in the normal modes, violates the Tsirelson bound, right, the classical bound, then you know that the two physical oscillators are entangled for that particular value of theta. The proof is, I'm not going to go through that in the interest of time, but it is proven through Wigner negativity. It turns out that if you have a violation, then the Wigner function is negative. So, yeah. There's also a numerical, but a global minima of sorts that we attain for all other theta using semi-definite programming. Here we plot theta against the violation itself, and we compute the log negativity of the states, log negativity of a function of the mixing L theta, and then the score. And of course, since this is a numerical exploration, you have a truncation as well, chosen such that you do have some amount of entanglement. So the dotted line represents the states that are entangled, and then the states that are not. Separates the states that are entangled from those that are not. Horizontal line cuts, that is, if you were to fix the values of the violation, you see that the total negativity of the states generally increases with theta, and vertical line cuts for fixed theta, the log negativity would increase with violation. And in fact, this part, the last pi by 4, where all the states are entangled, is what we proved analytically previously, right? With theta equals pi by 4, if there is violation, it is entangled. It's not the case for theta equals pi by 16, for instance, because there are so many states that violate but are not entangled. And finally, to compare our criteria with others, we picked a few to represent some classes of criteria where, for instance, Duan would be uncertainty-based and Hillary-Zuberi, again, positive partial transpose and whatnot. First, again, as was our motivating factor, is our criteria of classical states foolproof? Yes. So is Hillary and Zuberi.